Howdy, all, and howdy, all. Welcome back to the channel. I am Professor Parks, PhD, and we're going to talk about the night sky. Basically, what does it look like? What does it look like to you? What does it look like to me? What does it look like to somebody in Bangladesh? Hopefully, I don't have the sound issues that I did a couple streams ago, a couple lectures ago. So I'm hoping that somebody who's watching this will let me know. Actually, I'm going to pop over to the tubes. I don't think I have an audience at the moment. And I'm going to check because I don't want to have to go through all this and realize, oh, yeah, it ain't working. Whoops, wrong one. No, that's not what I wanted. Haha. Oh, all right, good. I'm good. Okay, sorry about that. Should learn how to text before I actually come on stream. Anyway, well, again, welcome back to the channel, and we're going in. This is a continuation of my lecture series on the solar system. And what I'm going to talk about today is I'm going to start off by talking about what the sky, when the Greeks looked at the skies, and I'm picking out the Greeks because my Western bias is showing. From a Western standpoint, the Greeks were the first civilization to really, one, catalog the sky, and two, offer up physical reasons for why the night sky appeared to function the way it did. And so I want to start off this lecture by talking about who are the major players, what did they do, and how is it that set essentially our worldview for the next 1,600 years, or actually roughly 2,000 years. So I'm going to start off with, so the big questions are, well, actually, no, let me take a step back, even further step back. The earliest astronomer that I'm aware of from a Greek standpoint was Hipparchus. Hipparchus was a gentleman who did a couple of rather fascinating, cool things, I guess. The first thing he did was that he completely cataloged the night skies that he could see it for the entire year. And he noticed a number of things which were, how should we put it, odd or in need of explaining. Hi, Judy. Obviously, it's not known how the folks around him thought about the night sky or, wondered how it works, because we don't have their writings. We don't know. They didn't write it down. We have basically what Hipparchus gave us. But for whatever reason, Hipparchus decided that he needed to quantify the sky. And what he did was that he, fairly accurately, at least visually speaking, he was able to map out the locations of every object in the night sky that he could see, their positions relative to each other. And he was able to basically categorize the brightness. And we're going to get back to that later on. We come up with a magnitude system, which is unfortunately a little bit counterintuitive. The basic idea is that Hipparchus decided that all the brightest objects in the sky that he could see, specifically the stars and the wandering planets, I guess, he said, all of the bright things in the sky, I shall call them first magnitude, of the first magnitude, of the tiniest, faintest little dots that I can see in my night sky. And again, this is ancient Greece, so there is no light pollution pretty much at all. So the tiniest things that he could see in the night sky, he said, I shall call these sixth magnitude. And then he subcategorized everything else that he could see in that sort of order, in that regime. So the next brightest stars were second, then third, so forth and so on. And it truthfully is at the time, particularly at the time, a rather subjective um, formulation. But it worked. It worked well enough. And I apologize. I'm still kind of getting over whatever this is. Might be the Rona. I'm hoping my tests are in today. Anyway. Oh, man. Excuse me. Woo. It was only until later that a guy by the name of Nathaniel Pogson decided to throw math at the problem, and he possibly arbitrarily decided that the first magnitude stars were 100 times brighter than the sixth magnitude stars, and then we can go from there. Astronomers then had a field day about, oh, now we can actually quantitatively say, that's a 1.5 magnitude star, that's a 4.2 magnitude star, so forth and so on. But getting back to Hipparchus, like I said, he mapped out the positions of the sky, and he noticed a few things that I'm going to go over, particularly the fact that the sky is not static. The sky does not appear to, isn't the same from night to night to night. It might appear so on a small time scale, like if you go out tonight and at 9 and look up at the sky, and you'll see various constellations. At this point, you'll see Orion, probably in your eastern sky. And then if you go out tomorrow, you'll see Orion pretty much in the eastern sky at 9. But if you wait and you actually observe, make observations over the course of, say, 6 months, you won't see Orion anymore. Orion appears to move in the night sky over the course of the year. And you'll see new constellations. The other thing that Hipparchus undoubtedly knew, although again, this I'm going out on a limb on, is that if you change your location, if you went more north or more south, the stars that you could see changed. If you went to the north, the number of different stars that you could see actually decreased. Whereas in the south, you saw more stars than you could see, individual or more different stars than you could see going in the north. The thing that I am so very impressed with Hipparchus is that given all that, given those observations, again by eye, actually he used a stick with a hoop. He was able to map out the sky, and he had a long enough observational lifespan that he actually noticed precession is a thing, or was a thing, which I'll go over later on, and it really blows my mind. It's pretty awesome that he was able to do that. So anyway, so we have this setup. We have this idea. All right, Hipparchus came along, basically mapped out the sky. Woo! Now, there was a lot of discussion, obviously, of what do we live on? We live on this big, seemingly flat rock, and the stars seemingly move. The sun, earth, moon, sun, moon, stars all seem to move above and below every night. So the question really is, the central question became, what is the center of reality? What is the center of the cosmos? And during this time, the general consensus was that the Earth was the center of all things because we live here, so it must be the center of all things. Well, around 250 BCE, there lived a guy by the name of Aristarchus of Samos. And he took this general idea that actually the sun is the center of the universe. The logical explanation for that is, or the logic that he used and expanded upon, was that the sun is so bright. The sun is the brightest thing in the sky. And so obviously something so bright and so luminous, that in fact must be the center of the universe. He then went on and actually did a rather nifty technique, which unfortunately requires very precise instrumentation to do, but you can geometrically determine how far away the sun is from the moon. He, by no means, apparently a stick with a hoop or whatever, is certainly not precise enough. So his estimation of the distance of the sun from the moon and then from us was woefully inaccurate. But he used the timing between the first quarter moon and the third quarter moon and was able to show a very simple geometric proof that that would give you the relative distances. Unfortunately, the angle that he came up with between the first and second quarter moons and the timing that he came up with, second, third quarter moon and the timing and such, he only determined that he estimated that the sun was only about 20 to 30 times farther away from the moon than the moon was from us. That's woefully inaccurate. Actually, that number is around 400. But it was enough to suggest that the sun was far larger than either the Earth or the moon. And that again solidified in his mind the sun must be, in fact, the center of all things. So he was actually the first heliocentrist back 250 BCE or so. And he believed that he also believed that the sun was a flaming rock, basically a literal burning rock in space. Of course, he got that wrong too. But why? But if you do any sort of research into history, in scientific history, you know that for a very long time we believed that the Earth was the center of the universe. So what happened? What happened was Aristotle. Aristotle came by about 200 BCE or so. I think I've got these dates right. And he used certain logic to basically say, no, Aristarchus, you're nuts. I'm glad you got kicked out of Alexandria. Good riddance to you. Aristarchus was not well received for his ideas and was exiled. At least he wasn't burned, as other folks were later on. Aristotle was a genius. He is really the foundation of physical science. His work, physics, is just groundbreaking in that it supplied the first time it was written down. He supplied a coherent, if incorrect, but coherent way of looking at the universe, of explaining how objects moved, what their inherent behavior or what their inherent natures were, so forth and so on. And so he took a little bit of umbrage about this whole idea of the Earth going around the sun, because from everything that he could see, everything was Earth-centric. If you drop something, it falls to the earth. Basically, all things go to the earth, and he believed that was part of the nature of matter, was to go into the earth, or at least some matter to go into the earth. He was the one who came up with the four elements. Anyway, but the thing that I want to really emphasize, because I think it's a fascinating part of the scientific exploration, is that Aristotle realized that there was a consequence, a observable or potentially observable consequence to a heliocentric model versus a geocentric model. How is it that you can actually tell that one thing is moving around another? Well, if you assume that the stars are fixed, if you assume that the stars are immobile, basically, the one way you can figure it out is if the sun were in fact the center of the universe, or let's put it more bluntly, if the Earth were revolving around the sun, then what we should see is that the stars should move relative to each other. So basically the idea is that the stars are this field of background stars. And if here is the sun, and I'm the Earth, this is going to go badly. When I look at the stars, I'm going to look at certain stars against that field of stars over here. if I go around, if I orbit around, now I'm going to go look this way. I'm going to see the stars along this side or in this field. This is a phenomenon known as trigonometric parallax, which I will go into a lot better detail later on. But that is the consequence of Earth going around the sun. If the Earth was stationary, then our position relative to the stars doesn't change. It's the sun that would experience this parallactic effect. And so they sought to measure that. They sought to see this. I don't know if they used Hipparchus's work or if they actually did it themselves, but ultimately they didn't see it. They did not see this stellar parallax. Now, the teaching moment here, and the thing I find to be fascinating, is that they were confronted with two options. Basically, this is sort of the scientific method. You formulate a hypothesis of this Earth must go around the sun, and you come up with a test, and that test is stellar parallax. And you come up with, and your observations do not bear that out. Now, you obviously have to rethink your hypothesis because your hypothesis has been falsified. But you really have two options to this. The first option is to do what they did, which is, oh, I don't see stellar parallax, so therefore the Earth doesn't revolve around the sun. The Earth is stationary. But the other possibility is that stellar parallax is tiny, is so small that they were not able to measure it using the technology that they have. From a psychological point of view, I find it very interesting that they were able to accept certain ideas about the universe, such as the stars were distant away from the Earth, and that there were planets revolving around the sun and or around the Earth and so forth. But the idea that the stars were really, really far away was something that they couldn't accept. And so Aristotle won, and the Aristotelian belief progressed and basically was king until the Copernican revolution, roughly around mid 1500s. And when I get into the Copernican revolution, I'll get into the reasons why it had such permanence, why it had such power. But so the Greeks settled on the fact that the Earth was in fact stationary and that all things revolved around it. They believed that all of the objects in the night sky were located on spherical shells around the Earth, and each shell moved independently of each other and were composed of this special matter called ether. So for Aristotle, you had earth, you had fire, you had air, you had water. Those were the terrestrial or earthbound, biggie, earth bound elements. That's what comprised everything that we see and experience. But the stuff in the space, that behaved differently. For one thing, everything seemed to move in a uniform motion, which we don't see really here because, friction and air resistance is a thing. And so obviously, if the things in the sky don't move in the same way that they do here, they must be made up of different stuff. And so he referred to that as ether. Now, I mentioned that they believed that these things were concentric spheres on top of each other. So while the Greeks believed that the Earth was stationary, they did believe that the Earth was round for at least two reasons. One, they observed ships disappearing from the bottom up as they sailed away into the Adriatic or the Mediterranean. And they reasoned that the only geometric way that would be possible is, in fact, that the object was going over a curve. that essentially it was going beyond the horizon and was disappearing over the curve of the Earth. The other, and perhaps probably the more convincing, I suspect, at least Aristotle, were eclipses, specifically lunar eclipses. There are great pictures or composites of a lunar eclipse as it's happening, and it's very easy, very clear to see the Earth's shadow across that face of moons, and it is very clearly a disk. And so, again, when Aristotle viewed eclipses, he reasoned that the only geometric shape, or he correctly inferred, for one, that what was happening was that the Earth's shadow was being cast upon the moon during these eclipses, and that's what actually causes them. And then, based on that, he then said, all right, the only geometric shape that should be casting that kind of shadow is, in fact, a sphere. So the Greeks didn't believe the Earth moved, but knew that the Earth was a globe. So let's talk about what they could also see, or basically, let's talk about the systems that were built in or about this time to describe this universe. Oh, let's do that. Nope, not that one. That one? That one. Yay! So, actually, I guess let's do this. So, as I said, the Greeks believed that the universe was comprised of differing shells. Here, we're going to concentrate on the furthest shell, and that is what we now refer to as the celestial sphere. We have taken something the Greeks thought was real, was in fact an actual physical shell, and we now use it as a conceptual tool to basically to represent a 3D universe or in 2 dimensions. The first noticeable thing about the celestial sphere, or rather, the first thing that the Greeks did, and many civilizations have done this, is that they saw patterns within the stars. Humans are really good at doing that. They're really good at finding patterns. If you don't believe me, then you need to find Roger from Mud Fossil University. He is fantastic at finding patterns that don't exist. But they saw these stars and they grouped them into patterns, and they referred to them as constellations. And typically these were used as storytelling devices, some way to confer the myths and culture onto previous generations. But while these constellations, while these stars may appear to be close together within the sky, that is almost always not the case. As I said, the celestial sphere is a 2D representation of a 3D universe. Let's take the constellation of Orion, for example. I have found that most people can identify Orion in the night sky. It's got the 3 little stars in the belt, yada, yada. Oh, and again, I'm showing my northern bias. People in the north can easily identify Orion. The big red star in the corner, in the upper corner, his shoulder is Betelgeuse. The big red or blue star on the bottom is Rigel. Like I said, when you look at it, they look fairly close together in the sky. But if you actually looked at the distances of these stars, they are hundreds, if not 1,000 light years different between them. They are in no way, shape, or form actually close to, or can be thought of as being close together. But again, this is due to projection. So we have these constellations, but we also have these things called asterisms. Now, asterisms, as I define, are either a subset of a much larger constellation, or are a combination of bits from separate constellations. So, strictly speaking, the Big Dipper is not a constellation. The Big Dipper is an asterism. The constellation is Ursa Majoris, the Big Bear, which you can see here on the left. It has a lot of stars that people really don't talk about. And for some reason, I don't know what the bears look like in ancient Greek, but this bear had a really long tail. I don't know. But the Big Dipper is only that tail and the back body of the bear. That is a classic example of an asterism. Another example of an asterism is the Summer Triangle, where we have the star Vega in the constellation of Lyra, the star Deneb in the constellation of Cygnus, and the star Altair in the constellation of Aquila. Those make up a very bright, very noticeable triangle in the night sky. In this case, light pollution actually does help because these are so bright relative to their companions that most of the time you can't see the companions. You can just see these three bright, stars in the sky. And yeah, look, summer triangle. And it's called the summer triangle because you can really only see them in the summer. So those are the things. So that is how we initially just group things. Now astronomers basically, I don't have a good slide for it. Astronomers have kept with the constellations, still use constellations today. There are 88 of them, north and south. And and you might ask yourself, why do astronomers actually care about constellation? It's because it's a good reference system. So we think of constellations very much like provinces or states or what have you. They are territories in the sky. So immediately, if I talk about a star that I'm studying in the constellation of Andromeda, like Lambda Andromeda, then any astronomer I'm talking to immediately has a conceptualization of where in the sky that is, and also when in the sky that is. When is that constellation viewable? And if you get into the nitty gritty, we've actually bounded these things, and it's really weird. It looks like a gerrymandered Republican gerrymandered state. It's odd. Anyway, so and these 88 constellations encompass cover the entire surface of the celestial sphere. There is no part of the celestial sphere that is not in part. There's not a part of the celestial sphere that is not in a constellation. So what is the celestial sphere? Well, let's talk about some of the characteristics, or let's talk about some of the key points or key positions. Really, the celestial sphere is, again, as I said, a projection. And in reality, it really is that. What you want to do, what was done, is we have a coordinate system here on Earth, longitude and latitude. We refer to the point at the top of the Earth, as the north geographic pole, and the bottom of the Earth is the south geographic pole. The poles indicate the axis of rotation for the Earth, and then you have lines of longitude which go from one pole to the other. And then you have lines of latitude, which are parallel and go up again from one pole to the other. And halfway through that basically marks the midplane of the Earth, is the equator. So what we've done is the celestial sphere is simply a projection of that. So you take the geographic poles, you extend them out to a arbitrarily large sphere, celestial sphere, and you now have celestial poles. The north celestial pole is right above the north geographic pole. The south celestial pole is right above the south geographic pole. Lines of longitude, when expanded outward, become lines of right ascension. Lines of declination, when lines of latitude that get expanded outward, those are known as lines of declination. The celestial equator, the equator, when expanded outward, becomes a celestial equator. And so here you can see again this model. This is the Earth is tiny in the middle. You can see these stars here, here, and here. The going straight up from the geographic pole, you get to the North Celestial Pole. South Pole gets down to the South Celestial Pole, and so forth. Again, you have the celestial equator. The other line, which is not a projection, which actually isn't a projection of a terrestrial coordinate system, is called the ecliptic. The ecliptic is defined as the path of the sun across the night sky, or rather, the path of the sun across this celestial sphere. And they noticed that that path is tilted relative to the celestial equator by an angle of 23.5 degrees. And I don't know who was the first person to write this down, but they realized, probably Hipparchus, they realized that that represented a tilt of the Earth, that the Earth was tilted with respect to the sun. We now use the ecliptic as astronomers now use the term ecliptic a little bit more broad, or in a little bit different way. When we talk about the ecliptic, what we're really talking about is no longer the path of the sun across the celestial sphere, but rather the plane that the Earth marks out as it goes around the sun. We refer to that as the ecliptic plane. And basically, we use that as a marker for measuring the inclinations and positions of planets in sort of three-dimensional space. For now, the ecliptic is simply the path. And you can see that here. This is the celestial equator. And then you have the ecliptic, which is tilted. As I mentioned with I mentioned right ascension declination. One of the things that you need, if you want to precisely and uniquely, I really apologize for this. God, my nose just won't stop. Oh. If you want to uniquely identify the location of something, then you need to use what is known as a coordinate system. And on 2D surfaces, like the surface of the Earth or the surface of the celestial sphere, that coordinate system requires two measures. For us, longitude, latitude uniquely identifies the position of a city. For the stars and the planets and the moon, celestial bodies, one such coordinate system is known as the celestial coordinate system, which is right ascension and declination. Much like the terrestrial longitude and latitude, right ascension and declination are invariant to the observer. A star is going to, like, for example, Vega is going to have a right ascension of 18 hours, 36 minutes, regardless of who you are, where you are. It is, in a way, an absolute reference system. Declination is defined by the celestial sphere, or the celestial equator. Lines of zero declination means that the object lies along the celestial equator. Declination goes positive as you go towards the north, and then negative as you go towards the south. Or it can be referred to as 30 degrees north declination or 30 degrees south declination, very much like latitude can be expressed. Right ascension is very much like the longitude system here. The 0 point of that is fairly arbitrary. For us, the 0 point is in Greenwich, England, because, the English were kind of imperial for a while. And they just said, hey, 0, the prime meridian is where we are. So they call it at zenith. They're at 0. The 0 point for right ascension is a little bit more physically defined. And I'll get more into that later on, but essentially the 0 point of right ascension is in the constellation of Aries, at a position which we refer to as the vernal equinox. Kind of getting ahead of myself here. Another coordinate system that we can use is the horizontal or the horizontal or as I refer to as the alt-as coordinate system. This is the one that's most natural to folks, I think, because it is based upon your locality. It's based upon you, really. And the idea here is that you have a local horizon, which is parallel to the ground. So we approximate that your local conditions are essentially flat, even though you're a globe. Oh man, cannot wait to get over this. So you have the horizon, which is basically flat. And you can envision a dome above you. You can envision a dome on top of you. The point directly above your head, the point at the top, the peak of the dome is the zenith. That is the point directly above you. If you were to look at I just had the word. If you had the opposite point to this, yes, Judy, that would be your own personal dome. The opposite point is called the nadir, and that is a point directly below you. That really is just a nifty bit of trivia because from an astronomical standpoint, it's really meaningless because you obviously can't see through the Earth, so you don't care about stuff that lies below your horizon. The next demarcation is known as the meridian. The meridian is a line that starts due north, or I guess it could start due south, but here we're going to start at due north on the horizon. It's going to go up from the horizon. It's going to pass through your zenith. It's going to go straight back down to due south. It's basically, it demarcates the eastern sky from the western sky. The special thing about the meridian is that anything that lies on the meridian, that is as high up in the sky as it's ever going to be during the night. Oh, guys, glad. Thank you, Roke. I am glad that I cleared that up. If a star is on the meridian, that is as high up in that it's going to be in the night sky. And what I mean by high up, what I mean is the two coordinates that we use for the horizon coordinate system, or as I call it, the alt-as, or altitude and azimuth. Altitude is simply a measure of height. You go from your baseline, or your 0 point is the horizon, is basically your flat plane. And then that goes up to 90 degrees at your zenith. So altitude ranges from 0 to 90, and it's always positive. You can have negative altitude, but again, that would be looking below the horizon, which we can't see anything, so it really doesn't make any sense to dwell on that. Really, all a negative altitude tells you is that it's below the horizon and you can't see it yet. Azimuth. Azimuth is the angle from north around through the east and then back again and then around. So if you look due north, that you have an azimuth of 0. If you look due east, you have an azimuth of 90. If you go due south, 180. If you look due west, 270, and then north is either 0 or 360, dealer's choice. And so any particular object in your personal dome can be described by both an altitude and an azimuth. So if I have something over here, then I would say that the altitude may be 36 degrees above the horizon and 57 degrees away from north, east of north. Those are my two things. The alt-as system is intuitively probably the most intuitive system that we have. The problem is that it's only useful, only applicable to a single observer. Depending on the precision of your measurements, it's not even useful to a person standing 6 feet away from you because they have their altitude and azimuth are going to be slightly different than that other person. You can imagine that if you are 1,000 miles, if you have two observers 1,000 miles from each other, they are certainly not going to agree where a star is in terms of altitude and azimuth. They will for a celestial coordinate system like right ascension and declination. Those like longitude and latitude are absolute. They are that is defined irrespective of the observer. The horizon system doesn't have that constraint. It is only useful for a one observer at their particular locality. Speaking of what I mean by, oh God, Lord, yeah, hot. Speaking of not agreeing as to what your position is or what star's position is from one locality to another, let's take some extremes. Let's look at what the night sky would look like if you were at different places on the Earth. And like I said, let's take the extremes. Let's say you're on, actually, I have a better slide for this. Oops, that's not where I wanted to go with that. Here we go. Imagine you're at the south, north or south pole. Doesn't matter which. You basically see the same idea. Is if you're directly at the north or south celestial pole, what you see is something that would really be weird. And that is the stars do not rise or set. If you're at the pole, the stars do not move in altitude. They move solely in azimuth. They go around you. No stars are going to set. No stars are going to rise. The stars that you see are the stars that you get. Those are the only stars that you will see ever in your life if you never move from that spot. It is the only time, the only location where you can see every star in the night sky that you will ever see in a single night. Nowhere else on the Earth can you say that you can say that to be true for every single star that you can see. So this is one extreme. Talking. Yeah, it is trying to talk to this head cold is not is suboptimal. Anyway, the term we use for stars that do not rise or set is circumpolar. If a star is circumpolar, then at your location, it does not rise, it does not set. You can always see it. Circumpolar is not an absolute characteristic. A star can be circumpolar in one location, but not circumpolar in another. As seen from this extreme, this is Quito, Ecuador. This is basically this is the largest city that's closest to the terrestrial equator. And you would see here, and I should say, I may not have, I took this for granted, but what you're seeing here, these white lines are star trails. What the person has done is they've taken a picture of the night sky and left the shutter open for, in this case, hours. And they have allowed the camera to expose upon the sky as the sky moves. Same sort of thing here, where someone looked basically due west or due east, I don't know, and left the shutter open and exposed on the sky for hours. And what they see are these star trails. And again, to me, this is phenomenal because it's so unlike my own personal experience. Here we have that the stars will go directly over you, so as arcs. So instead of going up, getting to a high point and then coming back down, these go straight up, straight down. They arc around you. So if you're on the pole, every star that you see is circumpolar. If you're at the equator, the only star that is circumpolar is Polaris. kind of. In reality, no, but within the within your eye or limitations of your eye, Polaris basically is at the North Celestial Pole, and that's going to be on the horizon. Every other star is going to rise and it's going to set. So all stars are rise and set. Now, as I said, the unique perspective of being on the pole is that in a single night, you can see all the stars that you will ever be able to see during the course of a year. The special condition around the equator, folks on the equator have the treat that they can see every star on the celestial sphere at some point over the course of a year. Now, obviously, during one night, they're only essentially seeing one half of the celestial sphere. The half of the celestial sphere the sun is not in. The sun washes out the stars that are behind it, essentially. Stars are there, we just can't see them because the sun is so bright. So on the equator, those folks can see every star in the night sky. There is no star that is not available to them. But for the rest of us mortals, we see something in the middle. We see something that is sort of a hybrid of the two, where you have, in this case, I can definitively tell you this was taken in the northern hemisphere, because I can see in the middle of that the bright point that does not seem to move. That is the star Polaris. It does not appear to move because it is very, very close to the celestial pole. And so you can envision this is a great way, at least for me, to envision that the celestial sphere is rotating, basically pivoting upon that axis point. Now I'm going to actually switch over to something else for a second. Oh, that's not what I want. And I'm going to switch over to this. So let me share this with y'all. This is an awesome website. Highly recommend it. It's the Nebraska Astronomy Applet Project. And here you can find astronomy simulations galore. You can find laboratory exercises if you want to challenge yourself. And I use it with my classes all the time. You can download the suite of if you have a Windows or Mac, you can literally download the application and run it locally. You don't actually need an internet connection to use it. But since I'm on a Linux machine, I'm going to do it the legacy way. And so what we're seeing here is these NAAA labs. And what I'm going to look at is the rotating sky. I'm going to go there. And then I'm going to bring up rotating sky observer. Let me make sure that this is being seen. Actually, I'm going to split this so that I can see that. All right. Where is it? There we go. Yay. All right. So this hopefully is a good representation of what I was talking about of the celestial coordinates versus the horizontal coordinates. And I can't see the chat, so let's do this. I'm probably going to miss out on the chat because my screen is not large enough. Oh, all right, let's do that. There we go. That actually is better. So here, what we have is someone in basically where McToon lives in Minnesota, for example, around a latitude of 40.8 degrees north and a longitude of 96.7 degrees west. So we have the Earth in the celestial coordinate system, RA and DEC. We have the Earth. We have our position on that sphere, and then this is our celestial sphere. On the horizon system, we have, this is us by this very magnificent stick figure. You can see north. Basically, this is your flat plane. Your horizon is your localized flat plane. North, east, south, west. Can I And so right now I have shown, so this circle, this gold circle here is the celestial equator. This zero here, or this gold circle here, is the 0 hour or the 0 position of right ascension. You can see that on the celestial pole, or the horizontal position or horizontal coordinate system, by the celestial equators here, and here is the 0 angle. One thing that is really nifty, and this goes towards celestial navigation, and I have to say that I really have my expertise as an astronomer. I have to say that it might seem a little weird, but celestial navigation really ain't my thing. Mainly, what I can tell you is that because of the serendipity of Polaris being where it is, basically at the North Pole, what you can see is that that celestial equator is going to be at a certain height relative to your latitude. So let's see. I don't think. Let me actually go back here for a second. No, Web Explorer. Nope, that ain't it. All right, so I know there's actually a better simulation for this, but I am going to just stick with the one I got. Did I do it again? Yes, I did. Going back to here. All right, so you can, so hopefully you can see, and I really wish there was a way that I could show you the angles here. You have an angle from zero, from the horizontal or the green horizon. You have an angle where this pole is, and that angle is equivalent to your latitude. So if you were the stick figure person, and you were to see Polaris, and you were to measure from due north all the way up its altitude, you would find at this location that it would be 40.8 degrees north, or 40.8 degrees above your horizon. So let me change this. Well, let me move this down, actually. So now hopefully you can see that if I go to lower latitudes, now I'm at 22 degrees. Polaris is now lower, and I can continue to play this game, where if I keep going, again, this represents basically a position on the equator. The celestial pole or Polaris is at the horizon. And then I can do the other extreme. Whee! Now, Polaris is going to be at your zenith. I'm at a latitude of 90 degrees. Oh, you never see Polaris? Yes. For those of you in the southern hemisphere, again, I'm showing my northern bias. If you are over here, say at 38 degrees south, you would see something like this. Basically, you would see, from my understanding, the Southern Cross is kind of your Polaris. You would see the Southern Cross over here, and you would see all things going around it. So let me do that. Let me just start poking stars on here. Whee, lots of stars. There we go. So now, if this is my really weird random star field, what I can do is over the course of let me keep going with what I was talking about. So you have this celestial, you have this. I was talking about the angle of the celestial pole, but you can also see a commensurate angle with the celestial equator, which is basically the opposite. So, for example, if I'm at the pole, Polaris is at my zenith. The altitude of Polaris is 90 degrees, equal to my latitude. The celestial equator is now on my horizon. It has an altitude of 0. So it is at my, what is it called? Co-latitude? I had the word just there, but it's essentially 90 minus that angle. So if the celestial pole or the celestial pole is at 90, then the celestial equator is at 0. If you're at, say, 60, then the angle from the horizon to the celestial pole, that's 60. The angle from the southern horizon to the celestial equator, that would be 30. And then you can do there, where now you're at the equator. The altitude of Polaris is 0. Altitude of the summer triangle is roughly 0. And the celestial sphere goes directly above your head. It is now at an altitude of 90, essentially. So let's put us where Judy is. Roughly around 63 degrees. .09. All right. Shoot. I don't know if it actually took that. 63.09. Not. Why does it not like that? Let's try 0.1. All right. Well, I guess I'll have to do it myself. Stupid. I think Judy's over here. Hey, I almost had it. All right. So, Judy, I'm putting you somewhere in Scandinavia. So this is a representation of what Judy kind of sees. And I'm going to start the animation. So what she's going to see is, and I'm going to, do I have star trails? No, I do not have star trail. Oh, yeah, I do. There we go. Boom, star trails. So this is what she sees. She sees some stars will rise, go overhead, and will set. She will also see Polaris way up here, and she will see these stars up here appear to go all the way around. So you can look at these regions. And so anything in this region is going to be circumpolar. And you can define that as anything that has a declination of 90, greater than 90 minus your altitude is going to be circumpolar. So in this example, I'm going to round up to 64. Anything that has a declination of 36 or higher is going to be circumpolar. It's always going to be in the night sky. Commensurately, if you have a star which is 36 degrees south on a declination or lower, you're never going to see it. It's never going to rise like this. So these are the stars. So the stars not in blue, these are the only stars that Judy can see at her location ever over the course of a year. So basically, those stars. All right, so let's flip this around. Now, I am going to, actually, judging by your name, I'm going to put you in Roque. I am going to put you in Argentina, Brazil, somewhere down here. And this is your situation. So, again, you see stars rising in the east, setting in the west. The Southern Cross would be somewhere here. Polaris is right back down here. Argentina. All right. So definitely not Brazil. Definitely not Brazil. So these are your, hopefully you can see that your circumpolar stars, your region of circumpolarity is smaller than Judy's. Because for you, anything that has a declination of greater than 38, so anything with a declination of greater than 52 I can do math. 52 is going to be circumpolar. Whereas Judy's was in the anything with a declination higher than around 30 some odd, those are circumpolar for you. Anything with a declination greater than 50 some odd south is going to be circumpolar. So the circumpolar region is much smaller for you than it is for Judy. So the stars that you can see are you can see many more stars than Judy can, or at least many more individual, or you have a larger collection of stars that you can see. All right. So that I think is sort of a primer on the celestial sphere and how you can see different stars at different times over the course of a night. And there will be some stars that you cannot see, and then there will be other stars that you see all the time, regardless of the time of year. Now, let me go back to this. Keep going. So here with the celestial navigation, like I said, you can use Polaris as a very good way of determining what your latitude is. And in a more complicated or more involved method, you can actually determine your longitude based on the stars if you have an accurate clock. So if there was an astronomer on the plane, then the folks in Lost wouldn't have been so lost. And here I am going to beg your forgiveness. I have reached my limit for today, and so I've been. So what I want to do is I'm going to post the rest of this lecture tomorrow at noon. I'm going to start it at noon. So same time that this lecture started today, I'm going to finish this lecture off tomorrow at noon. So I hope you. So yeah, I apologize for that. It's just I'm running out of steam with this, and so thank you all for being here. I hope this was informative. I hope you find this educational and fun, enjoyable in some way. If you do, if you like this sort of content, if you like the things that I do, please like, share, and subscribe. I am now always going to start to mention my Patreon. I do a great deal of outreach here at George Mason, and in order to help those, to aid in those endeavors, I have a Patreon. If you choose to become a Patreon, there are certain benefits that you can accrue based on what level you want to donate. Even at the lowest level, you may have the chance of having my firstborn child named after you. Again, caveat, assuming my partner agrees to that. All proceeds go to the GMU Observatory. So anyway, thank you again, and clear skies. Peace out. I hope you have a great rest of your day, and I hope to see some of you, if not all of you, back tomorrow, where I will talk about how the sky changes based on the year, and also what it is that actually causes the seasons. Spoiler alert, it has very, very little to do with the distance of the Earth away from the sun. All right. Bye, all.